Hi everybody, this is a warm-up problem, so make sure that you try the problem in My Open Math that should be very similar to this before you watch the video, and then check this out just to make sure that you get some of the highlights and get the idea of where we're headed with everything. So our goal right now is to work towards finding the derivative or instantaneous rate of change. And we've still got just a couple of steps to go. So right now we're working on the velocity and tangent problems, and they are related, so we'll work on them both together. So tangent, we're talking about tangent line, which is a line that just touches the curve at a single point. So for example, we could have a line that just touch the curve at t equals 2.5. We've already talked about the idea of having a secant line where we would say, okay, well, here's a second point. Let's connect the dots. There's our secant line. I missed a little, but you got the idea. For a tangent line, what we want to think is not that we're using two distinct points, but that we're trying to draw a line that just touches the curve and matches its steepness as closely as possible. In this section, we just want to really build up this idea of what is a tangent line and how can we estimate what our tangent line is or our instantaneous rate of change is. So we're going to try and work our way up to this. We're going to go back to average rate of change and slope of secant line and kind of build up this idea throughout this section. The first question we have in this problem is just asking us to describe the behavior of the ball on a couple of different time intervals. So the first one is t equals 0 to t equals 1, which is this stretch. And just something broad was fine here. I would just say the height of the ball is increasing on that time interval, or the ball is going up on that time interval. One thing that I think is important to realize here is that this is time and this is position, this is height. So this is not horizontal distance and vertical distance. The ball didn't necessarily follow this path. This is height and time, so the ball definitely went up and came back down, but it could have done that without covering any horizontal distance. So try to avoid that possible confusion where you picture this and think this is exactly what the ball did. The second part of this question asks us to talk about what's happening from t equals 1 to t equals 3. So that's going to be the other side of this parabola, and I would say something along the lines of the ball is falling or the height of the ball is decreasing for second 1 through 3. The last little bit is just what do you think is happening right at the instant that t equals 1? So this is the ball is right at the top of its trajectory. So I think for now, if that's all you said, that's great. But I think one interesting thing to start thinking about is what about the ball's height increasing versus decreasing? Right at that peak, it should be doing neither one of those things. So technically the ball has to actually come to a stop right at the top of its arc and then turn around and start heading back down. Okay, the next part of this problem is going to build up this idea of what average rate of change means in this context. So we're given a formula, but I hope that you recognize average rate of change in there right away. This is really asking us for the average rate of change of our position function s on the interval t equals 0.5 to t equals 1. So it's getting called AV, but it is average rate of change. So we need to know what s of 1 and s of 0.5 are to calculate this. And s of 1 is going to be 64 minus 16 times 1 minus 1, which is just 64. S of 0.5 is 64 minus 16 times 0.5 squared. So that's 1/2 squared, which is 1/4. And 1/4 of 16 is 4. So I'm seeing 64 minus 4, which is 60. So when I set up this AV, I'm getting S of 1, 64 minus 60 over 1 minus 0.5, which is 4 over 0.5. And remember that dividing by 1/2 is the same as multiplying by 2, so that should really be 8. So my answer here is 8, but we want to think about what it means. We want to explain its meaning in context. So if I'm looking back here, the 64 minus 60, those were s values. So those were heights, and the units on that were feet. And then the 0.5 is the change in time. So here, this is a delta S. If we want to use some of this change in notation, change in S or delta S. This was a delta T, which is time, and that was in seconds. So my units on this should be feet per second, feet divided by seconds. So what we really learned is that 8 feet per second is the average velocity. I would say from t equals 0.5 to t equals 1, the height increases by an average of 8 feet per second, or the average velocity of the ball is 8 feet per second. So I want to pause here to generalize. What we can say now is that in general, if S of t is a position function, then the average rate of change given by S of b minus S of a over b minus a will always give you average velocity. So that's kind of handy. If you're starting with something that's not a position function, this isn't going to work. But if your original function gives you height or distance traveled or anything along those lines, your average rate of change will always tell you an average velocity. Okay, so those are the highlights from this problem. And then we'll go ahead and jump into starting to work in a little bit of the calculus.